Young children, in the last classes we were seeing about the refraction at convex spherical refracting surfaces when light passes from rarer to denser as well as from denser to rarer. The same thing applies for concave spherical refracting surface also. This is a concave spherical refracting surface when light passes from rarer to denser, and we get the same formula, that is mu1 by u plus mu2 by v equal to mu2 minus mu1 by r. Similarly, when light passes from denser to rarer, this is denser and this is rarer, we get the same formula as we got for convex spherical refracting surfaces. That is, in place of mu1 we substitute mu2 and write minus mu2 by u plus mu1 by v equal to mu1 minus mu2 by r. The same thing applies for convex as well as concave spherical refracting surfaces. Now, when we combine the two refracting faces, we get what is called as a convex lens. Convex lens. We combine the two faces and we get what is called as a lens, and this is a convex lens. So a lens is a portion of a transparent medium bounded by two refracting surfaces. If both are spherical refracting surfaces, then we call it as double convex lens. If one is plane and the other is convex, we call it as plano-convex lens. If one is concave and the other is convex, then we call it as concavo-convex lens. Similar is the case with concave lens. If both surfaces are spherical or both faces are spherical, we call it as double concave lens. If the first face is plane and the second is concave, we call it as plano-concave lens. And if the first surface is convex and the second face is concave, then we call it as convex-o-concave lens. So like this we have different types of lenses. Now we are going to see about the lens maker's formula. Lens maker's formula is a relation connecting focal length, refractive index and radius of curvature of the two faces of the lens. So now let's start with lens maker's formula. We are going to see the same equations which we saw earlier. So this is a convex lens. We are seeing it for a convex lens. The same applies for concave lens also. So this is a convex lens. So before going into the lens maker's formula, we just see what is the optical center. Optical center is a point on the center of the lens so that a ray of light passing through it goes without any deviation. So that point is called as the optic center or optical center. Optic center is a point on the lens that is in the middle of the lens such that a ray of light passing through it goes without any deviation. The principal focus is the same as we studied for mirror. Suppose if you have a convex lens of a ear, parallel rays of light after refraction from the lens converges at a point on the principal axis, and this point is called as the principal focus. This is the optic center. This is called the principal focus, and this distance between optic center and principal focus is called the focal length, and it is positive for a convex lens. Similarly, for a concave lens, parallel rays of light after refraction from the concave lens appears to, see, it's getting refracted. After refraction, it appears to diverge from a point on the principal axis. This point is called the principal focus, and this distance is called as the focal length, which is negative for a concave lens. Now, the sign conventions which we have used is the same for both convex lens and concave lens. That is what we have used for mirrors, we will be using over here also. The assumptions that we used in the last class will be applicable for this figure also. Now, let us consider a convex lens. This is the optic center. This is the pole of this surface. Let us name the surface lens as XY. This is P1. This is the pole for this surface, and this is the pole for this surface. Now, we consider an object to lie on the principal axis. It is a point object. A ray of light from the point object gets incident on the face XP1Y at the point A. Now, if this surface was the only surface present and if the second surface was not there, refraction takes place at this surface XP1Y and we get an image formed at I1. We get an image formed at I1. So, for this surface XP1Y, where light is coming from rarer to denser, it's coming from rarer to denser. Here the refractive index is mu1 and for the glass it is mu2. So, this will be the object distance, that is u, and this will be the image distance, that is v dash, for this point object over here. So, a ray of light from O after refraction in the absence of the second surface forms an image at I1. So, this is the object distance and this is the image distance. Now, when you drop a normal at this point, for this surface, this is the center of curvature, will be to the right. So, when I drop a normal over here, this will be the center of curvature. You can see that the ray is bending towards, the refracted ray is bending towards the normal because it is from rarer to denser. So, the equation for this surface as we studied earlier is minus mu1 by u plus mu2 by v equal to mu2 minus mu1 by r. Now, let r1 be the radius of curvature of this surface and r2 is the radius of curvature of the second surface. Now, let us substitute for this surface minus mu1 by u plus mu2 by, here v is represented by v dash equal to mu2 minus mu1 by the radius of curvature for this, that is P1, C1 will be equal to R1. Let us name this as equation 1. But we know that we have the second surface is also present. So, refraction takes place at the second surface. For this, the final image is formed at, see, refraction is taking place at this surface. For this, the final image is formed at I. So, for this surface, refraction is taking place and the image is formed at I. Therefore, this distance is taken as V. That is C, that is from the, all distances are measured from the optic center. So, Ci is taken as V. Now, for this surface, we need an object. Now, this is the refracted ray. It is getting refracted along AB When extended, it appears to come from I1. So I1 is the virtual object for this surface whose final image is formed at I. Therefore, this distance will be the object distance for this surface. So, for the second surface, when the light is coming from denser to rarer. So, this is denser, this is rarer. And when we drop a normal, you can see that this will be the normal at this point. When we draw, this is C2. And you can see that the ray is bending. This is the normal. So, the ray is bending away from the normal because the light is passing from denser to rarer. So, when we use the equation for denser to rarer, which we have already proved, it is minus mu2 by u plus mu1 by v equal to mu1 minus mu2 by r. Now, let us substitute for u and v. Here, this is the object for this surface. So, this is the object distance. So, I write it as minus mu2 by v dash plus mu1. V is the image distance equal to mu1 minus mu2 by the radius of curvature of this surface is r2. So, I write it as r2. So, in order to make my calculations earlier, I just multiply with a minus sign and I get this as mu2 minus mu1 by r2 with a negative sign over here. I just multiply with the negative sign. So, I get mu2 minus mu1 by r2. This is also mu2 minus mu1 by r1 and this is equation 2. Now, let me add the two equations. When I add the two equations, I get this is 1 and this is 2. Let me write this equation once again. Minus mu2 by v dash plus mu1 by v equal to mu2 minus mu1 by r2. Minus of mu2 minus mu1 by r2. Now, let us add 1 and 2. When you add 1 and 2, we get this is minus mu2 by v dash and this is plus mu2 by v dash. It will get cancelled. So, the remaining will be minus mu1 by u plus mu1 by v equal to mu2 minus mu1 into 1 by r1 minus 1 by r2. Or let me take this mu1 outside. I can write this as 1 by v minus 1 by u equal to mu2 minus mu1 into 1 by r1 minus 1 by r2. Or let me bring this mu1 here. I get 1 by v minus 1 by u is mu2 by mu1 minus mu1 by mu1 into 1 by r1 minus 1 by r2 or 1 by v minus 1 by u equal to mu2 by mu1 minus 1 into 1 by r1 minus 1 by r2. As we all know, 1 by v minus 1 by u is called as the Lenz's formula and it is equal to 1 by f. So, 1 by f equal to this mu2 by mu1 can also be written as mu21 minus 1 into 1 by r1 minus 1 by r2, or in general I write 1 by f is mu minus 1 into 1 by r1 minus 1 by r2. This is the lens maker's formula for a convex lens. This is the relation connecting focal length, refractive index and radius of curvature of the two faces. The same formula is applicable for concave lens also. This is the same formula for the lens maker's formula for a concave lens also.